Good afternoon and welcome to Advanced NMR Spectroscopy course. Today I'll continue with the recording of 1D NMR spectrum. So yesterday I have told about various parameters to be set to get a 1D spectra or recording a spectra in a NMR machine. So these things are summarized here. Okay, so first thing is that you have to put the sample, you have to maintain the temperature, you have to adjust the temperature, and then you have to call the sim set, then you have to do the simming, adjust the homogeneity and all these things, and then you have to finally do a scan, and you have to do a preliminary scan with a large spectral width, and then you decide what will be your final parameters, including your spectral width and other thing, to get a spectrum with sufficient signal to noise ratio. So today we will continue with that. So what we will do in the last class, we have seen that we are getting the signal which is coming from the receiver coil. Okay, and that signal is sampled. Okay, it's a periodically sampled, and it passes through the amplifiers and it gets amplified, and this amplified signal is then converted from because that is analog sample analog data, so it is converted to a digital data by analog to digital converter. The resulting number, whatever we are getting from this ADC, it is the represent the signal intensity versus time. Okay, so that is nothing but your FID. Okay, and if you do a Fourier transform of this time domain data, you get the frequency domain data, which is nothing but the signal intensity versus frequency, which is shown here. So this is the FID of toluene. This is the FID of toluene. If you do the Fourier transform, you get the frequency domain data. Frequency is, see, I have shown here into the ppm, but one can convert the ppm into hertz unit depending on which machine you are using. Okay, so it is same actually. Now we know that this Fourier theorem states that every the Fourier theorem states that every periodic function may be decomposed into series of sine and cosine functions of different frequencies. Okay. Okay, so you see that whatever data you are getting, so it can be converted into a cosine function and a sine function. And if you do all kind of mathematical manipulations, I'm not going to detail into the Fourier transformation mathematics. The final form comes as this is the functional form of the final form, where this tk is nothing but it represents the kth point of the time domain FID data, and Fj represents the jth point in the resulting frequency domain spectrum. Okay, so each Fj point, okay, so this Fj point will be from 0 to n minus 1, because it will start from 0. Okay, so total number of points will be n points. It requires, so that is done by during the your Fourier transform. This requires a summation of all over all n points in the FID curve, and the total calculation involves n square multiplications and addition. So it's a very complex mathematical process, so it requires a computation. Okay, and nowadays this is done very quickly in a because the computers have become very fast now, so it can be done more or less very short time. Okay, and this Fourier transform process, which we are managing this NMR data, is using a Coulomb Take algorithm. Okay, so this is the algorithm where this for that what we have to do is that the number of points of the spectrum must be a power of 2 to the power n. Okay, that has to be. And yesterday we have seen that normally we get the data and around 2 to the power n range only. Now let us see how the typical Fourier transform of various popular functions using the Cooley-Take algorithm. So I have shown here, suppose if you have a plane cosine wave, okay, so you get if you do a Fourier transform, you get two delta function. Okay, that if you remember now, because see it cannot distinguish between the positive frequency and the negative frequency, that's why you get always two things. So you will get a positive frequency, you will get a negative frequency. Suppose if you have a decaying exponential curve, okay, so you will get a so this is you can consider like your as a on resonance, because there is no so on resonance means the magnetizing decays exponentially in the y-axis only, where the detector is fixed. Okay, so you get a clear cut NMR Lorentzian line. Okay, and I told you that NMR lines are all Lorentzian function. Okay, so if you do a Fourier transform of well-simmed sample containing a single frequency, then you exactly like in this case here also you get the two. So it cannot distinguish between the positive and negative frequencies. Okay, although it is a single frequency only. Okay, so that's why we need a quadrature detection. Okay, and that I have explained you in my last class. So how we are doing a phase shifting of we are splitting the signal, and then we are doing a phase shifting. So one is cos function, and is a sine function, and then we are mixing with our reference frequency, and then finally, so we can find out. Okay, now but you are taking. Suppose if you take only this FID, okay, so you get two signals. Okay, now if you do a pulse, this is like your pulse. Okay, so if you do that, so it is a step function which gives a sync function, which is you can see the characteristic wiggles. Okay, so these are the characteristic wiggles of a step function. Okay. Now see, sometimes you see that this is a very important thing why I'm telling you this. In this case, the FID has not decayed properly. So this is a very important thing. Suppose if you are recording NMR and if your FID has not decayed, and then you will see a wiggles. You can see that again, it is the same cosine function. Okay. Like your previous like this FID, but here see, because it has not completely decayed, so you are getting wiggles. Okay, so this is the general thing. Whenever if the FID has not decayed properly, you will face this problem. And if you take a Gaussian function, it will lead to Gaussian only. So these are the common signals which we process during NMR processing. Now after FID, so if you do after you receive the FID, and if you do the Fourier transform, okay, you never get you will get a spectra like this. Okay, you will see that the phase of the peaks are not proper. Okay, so that's why whenever you record, you have to do a phase correction. Okay, so now let us see what is phase correction. Okay. So if you remember the in my 2-3 I think second slide, I told about that the Fourier transform can be decomposed into a cosine transform and a sine transform. So the cosine gives you the real part and the sine gives you the imaginary part of your signals. Okay, and these real and imaginary parts of the signal are stored in separate memory locations. Okay. So the real part that is used for displaying spectrum, whereas we don't normally we don't use the imaginary part, but not necessarily that your the real part will be always absorptive. So this if you see this line or this peak, it is a fully absorptive peak, whereas you can see the other one is a dispersive. Okay, so this is a dispersion peak, and this is a purely absorption peak. Okay, now let us see what is the reason for why you get a absorption peak and when you get a dispersion peak. Okay. Now the phase of the signals. So when the phase of the signals after Fourier transform, okay, it depends on the first point on the FID. Okay, so from where it started, the first point of your FID, that decides. Okay, so let us say your signal is just along the at time t is equal to 0. If your signal is at the time of recording, see, time 0 and time of recordings are not same. Okay, when your recording time t is equal to 0, if your signal lies along the y-axis where the detector is there, okay, you get a purely absorption signal. Okay, because it is a cosine modulated signal. Okay, but let us say at the time t is equal to 0, your signal is not at the y-axis, but it is, let us say, it has moved to x-axis. Okay, it is not that. So at time is t is equal to 0, it is at x-axis. That doesn't mean that, see, when you give a pulse, everything comes to y-axis first. Okay, and but it depends on when you started your acquisition or started recording your spectrum. So by the time, let us think that it has moved to a x-axis. So in this case, you will see that because your detector is here, okay, so you will get a dispersion mode spectrum. Okay, or this looks like a sine module, because you can see there is a phase shift, okay, of 90-degree phase shift. So it is like a sine modulated spectrum, and you will get a dispersion. Okay, so to get the phase corrected spectra, okay, you have to do a phase correction, and nowadays it is done routinely. There are automatic routines in the NMR spectrum, and if you give a command, it does automatically. You need not to do it manually, or if you wish, you can do it manually also. So you first do by automatic phase correction, and then you can do manually if the phase correction is not proper. Okay, so there are two types of phase correction. One is the zero order. Okay, so the zero order phase correction applies the phase changes to all signals in the same way, because this zero order phase correction arises because the absolute phase of the signals at the detector depends on the cable length. Okay, so between your the receiver and the processing, so there is some length of cable is there connecting, so that actually causes some misphasing of the signal, and so automatically it happens same way to all signals. Okay, so it is very easy to do. So you will see that if it is for zeroth order, you will see almost all signals are very similarly or off phase. Okay, so if you do a zeroth order phase correction, okay, you will get the again purely absorption signal. Okay, but in case of first order phase correction, okay, if you do a zeroth order phase correction, you will see most of the some signals will be still in the not in the proper phase. Okay, so then in that case you have to do a first order phase correction. Okay, and it applies to a phase change whose amount increase linearly with the distance to the reference signal or the transmitter frequency. Let us see this is your transmitter frequency. Okay, or we will say that this signal is on resonance. Okay, so with respect to this, all other signals which are offset to it, depending on whether it is a positive offset or negative offset, there will be some error, and that will be frequency dependent error. So some cases you will the dispersion mode is more, some cases the phase is slightly off, depending on that. And if you do the first order phase correction, again you will get the properly absorption signal. Okay, so now why this phase correction thing is coming, specifically the first order phase correction. So when you do the 1D experiment, there is a time gap between the B1 pulse so there is a time gap between the B1 pulse and the acquisition of the FID. So you remember that in our pulsing and data collection, it is done on the same coil. Okay, so once you give the B1 pulse, immediately you cannot start recording the signal, because then it will be, because your electronics will then start recording some amount of signal from the pulse. Okay, so that's why there will be a small amount of delay. Now, as soon as you bring the magnetization into the y-axis, those nuclei which are on resonance will remain in the y-axis. Okay, for them it is not a problem, but for the nuclei which have a different, or those who are having offset, they will start processing, because as soon as the B1 field is off, they will start processing either in the clockwise direction or anti-clockwise direction, depending on their, if they are having a negative offset, they will go anti-clockwise. If they are positive offset, they will come clockwise. Okay, so there is a protection delay. There is a protection delay to avoid this detection of the pulse. Okay, so during that you will see that there is a precession there, because the spins has already moved to a new position depending on the offset, as I told you, and then you are starting the sampling. Okay, so that's why you will see that, let us say, if there is no delay time between the pulse, this is your pulse and this is your collecting the data. See, you will get clearly this is the signal from your reference, which is a on resonance signal, and which is any other offset signal. Okay. But as there is a delay time, once you give a delay time, so what will happen? You see, delay time means this is the pulse and then there is a gap, that is called the delay time. That may be in some microsecond or like that. Okay, so during this delay time, you see that which signal which is on resonance, it still is there in the y-axis where the detector is there, but the other one which is having a positive offset, that has moved to different extent. Let us say in this case it has moved to 90 degree. So you will see a pure absorption signal for the reference, that there is no change. Okay, because it is on resonance. But the other signal which has moved in the clockwise fashion will have a different phase. Okay, so that is the origin of the first order phase difference, and first order phase correction is done, and it depends. That's why if you see, it depends on how much of that magnetization vector has moved from the y-axis. Okay, and that depends on the offset value. So that's why I told you, it depends on the this first order phase correction. It depends on the offset value of the signal. And as I told you that already, they can be done using the routine available in the computer program of the computer of NMR machine. That okay. Now coming to, now there is also a, so if you want to improve the resolution of the spectrum, there is a process called zero filling. Okay, zero filling means you are putting additional data. So what is zero filling? Zero filling is the process of adding data points, okay, to the end of the FID. So what happens at the end of the FID? You do not have any signal, so signal intensity will be zero. Okay, but still you are collecting the sampling the signal. Okay, so that's why those intensities will be zero. You are putting the data points, but there is no signal, but still you are collecting the data. So that's why it is called the zero filling. Okay, so you can, that means you are collecting the FID for a longer time before Fourier transform. Okay, keep on sampling the your FID for a longer time beyond where there is no signal is coming. Okay, so so this zero filling can improve the data quality. Okay, as you are increasing the number of points per ppm. Okay, in the process data to better define the resolution. Okay, so you see this in the first case. So this is your FID, where the FID there is no more signal is coming. Okay, so you will get if you do a Fourier transform, you will get a spectrum. Okay, but if you see that the natural line width is now governed by the T2 star, effective transverse relaxation rate. Okay, now what you are doing, same FID, you are adding 5 times of data points. Okay, this is a 5 type, you are making now 5 times. So your FID is end here, which is nothing, that this point is now here, and beyond that you have collected your you have sampled your data. And if you do a Fourier transform, now you can see the unresolved peak in this case is now well resolved. Okay, so that's why you can improve the resolution by zero filling. So you can do a zero filling, you can do 2 times, 3 times, 4 times. Okay, normally in a recording, after a recording, one can do 2 times. 2 times is good enough for that. Okay. So that so one can find out what should be the theoretical resolution of FID is depends on the spectral width by and the number of data points. Now, as you are doing by zero filling, you are increasing this. So if you increase this, that means the resolution will increase. But there is a limit. Okay, okay. During this thing we are not talking about the relaxation effects, because you cannot get a better resolution than the which is governed by the T2 star. Okay, so now let us see there are other some other points in NMR spectrum. One is called the line width and the line shape. Okay, as I have told that if you do the Fourier transform of FID, you got always a Lorentzian line. Now, if you see the FID, so there are a couple of things. So important feature of the NMR peak is that its position. So what decides the position? So the position is decided by this period of this FID. Okay, so so this gives you the new I position. Okay, or the period of FID gives you position of the line, or this is the position of the line, or delta nu I. Okay, and then beside that the peak will have intensity and area under it, and that intensity and area under it, so it is governed by the T2 star as well as the height, this initial amplitude of the FID, this A, the initial amplitude, this is called the A. So the peak in the line intensity will be proportional to pi into this amplitude into T2 star. Okay, T2 star, I have already told you what is T2 star. Okay, so and the area also will be governed by that. Okay, and the shape means we will always call that what is the half width, we call that is the half width, or the frequencies covering in the half width. Okay, and that is actually again governed by the effective spin relaxation time. So this effective spin relaxation time gives you the half width, what will be the half width of the peak, what will be the intensity of the peak, and what will be the area will depend on the initial amplitude of the FID as well as the T2 star. Okay, so this new half is a measure of the uncertainty in frequency. Okay, okay, and it is inversely proportional to the lifetime. Okay, so if you so that's why the T2 star is very easy to find out from the peak shape. Okay, so half width will give you the from half width you can find out the T2 star, or 1 by T2 star equal to half width. Okay, but if you see normally the half width of the for the solution samples are between 0.1 to 0.5 hertz, depending on the sample and the field homogeneity. So how the magnet has been seen, and the quality of the sample constant. There are several things: percentage of the sample, temperature, many parameters are there, but it comes within that. So that means if a coupling constant which are less than 0.5 hertz, Okay, may not be seen, and that's why normally if the coupling constants are less than 1, you may not be able to measure them accurately. Okay, now that describes the what are the ways we actually process the data, once how we get the data, how we optimize the data, how we process the data, and how we get the NMR. Now let us see, as we were talking many times, that pulse length. Now specifically we call a 90-degree pulse. Okay, so how do we know that what is 90-degree pulse? Okay, so that we done, it is called the calibration of the pulse length. That is a very important exercise one has to do when you change a probe and or sample or solvent. Many specifically when you do a 2D NMR, before that one must find out the pulse length or calibrate the pulse length. Okay, so pulse length is that it is the flip angle alpha, if you see. Okay, is proportional to the pulse duration or pulse length. Okay, and that depends on the B1 also. So this is the your flip angle alpha. You can see alpha is related to the pulse duration or pulse length, and these two, you know that these two, the B1 is the applied radio frequency field, and gamma is the gyromagnetic ratio. And if you just convert into various units like gamma, B1, tau, you can gamma B1 is nothing but your precessional frequency under the applied field B1, and that is nothing but omega 1. And you can convert them, if this is in radian, you can convert into degree by dividing by 2 pi. And also when you we know that when you give a pulse, okay, so let us say the magnetization from Z axis to move to a new position, we don't know, it can be here also, it can be here also, even beyond this also. Okay, so at any angle, so there will be a, see, depending on how much it is rotated, there will be angle from the Z axis. That angle is called alpha. So that when it is rotated, then there will be a Y component magnetization and Z component magnetization. So the Y component magnetization is M0 sin alpha. This also I have told you earlier, and the Z component is M0 cos alpha. Okay, so for calibration of pulse length, what you have to do, so you have to do a pulse acquire experiment by increasing the pulse length. Okay, so let us say you have the B1 is constant for a particular, before you do that, you have to fix your B1. Okay, we know the gamma 1 is also fixed. Now, so what happens? The alpha is directly proportional to pulse duration. Okay, so what you can do that so if you change the alpha, okay, so that will, if you change the alpha, so that will change the value of sin alpha. Sin alpha means automatically the Y component magnetization. Y component magnetization means you have the detector here, so the detector signal will change. Detector signal can be positive. Now because it is in the positive direction, it will give you a positive. It can be suppose this comes this side, you will get a negative signal. Okay, okay. So when the pulse length, now there could be two situations. One is that this is your 0 time. Another time is that your magnetization is along the minus Z axis. Okay, okay. So, and another thing is that it rotated back to this position. So you will have a 0, then 180 degree and 360 degree rotation, means one full rotation. So what you will see, your detector will not see any signal. Clear? Because when alpha is 0, this Y is sin alpha is 0, so this is 0. When alpha is 180 degree, then also Y is 0. When it is 360 degree, also Y is 0. So that is the thing I am telling you. When the pulse length correspond to 180 degree or 360 degree, 0 degree or the initial, a 0 crossing of the signal is observed. So you will not, so automatically if you keep on increasing the the pulse, the duration of the pulse, you will see that initially it was 0, and then you will see it will increase, and then it will go to negative, and then again it will become 0, then again you can see that I have shown it here. If you see that signal intensity, if you see when it is a 0, the signal is 0, and now slowly as you are increasing the pulse duration, the alpha is increasing, so there is a increase in signal. When it is 90 degree, it is maximum, and then beyond 90 degree again it started decreasing. Okay, so and it becomes 0 at 180 degree. You can see this, and then it will become negative now because it is in the after this, you see now it will be detect the your signals will be in the minus y, so you will get a negative signal. Okay, and then finally you will become 0, which I have not shown it here. It will be like this. Okay, so this is your 0, this is your 180, and this is 360. Okay, okay, so you can find out the duration or time duration where the signal is becoming 0, either at 180 degree or 360. So you have to do a series of experiments. You take the NMR sample, keep on recording spectra with changing tau value, or the pulse duration you change incrementally. You will see that initially there will be a increase in signal, and then you see there is a decrease in signal, and then again you will see there is an increase in signal, then you will see there is a decrease in signal. Okay, so this corresponds to 0, this corresponds to 180 degree, and then you will see that this is corresponds to here somewhere 360 degree. Okay, so now if you have this, okay, so if you know the 90 degree pulse or 180 degree pulse or 360 degree pulse, where there is no, you will not receive any signals. Okay, so you know, so why, that's why you have to do a full circle. Otherwise you sometimes you don't know whether you are choosing the 180 degree or 360 degree. Okay, so once you know this is 180 degree, you just divide it by 2 will give you 90 degree pulse. Or if you take the 360 degree divided by 4, you will get the, it is simple mathematics. So I have shown you one example here. Okay, so see, this is the so while pulse length measurement, the null conditions were observed at tau value of 15.5 microsecond and 31 microsecond. So that means null point means 0 signal intensity. So the question is that how to find out the tau for 90 degree pulse or tau for 30 degree. It is simple. So this, as you can see, this is for 360 degree, because it is required double, and this is for 180 degree. So you can use any one of these value to find out. So 90 degree will be half of this. Okay, and 30 degree will be 1/6 of this. Okay, now from here, how to find out, calculate the V1 field strength. Okay, you can also find out the V1 field strength, as you see that alpha is equal to gamma gamma B1, and then tau p, okay, is equal to omega 1 tau p. So we have to find out what will be the omega 1. So omega 1 will be alpha by tau p. Okay, now alpha, we know alpha is let us say so alpha is pi. Okay, and tau p is 15.5 microsecond. Okay, or if you, this will give you omega 1 in radian. Okay, you divide it by 2 pi, you will get in, so you will be pi divided by 15.5 into 2 pi, it will be in degrees. Okay, sorry, it will not be in degrees, it will be in hertz. Okay, and if so it will be 1 by 15 point, sorry, this is not sorry, this will be 15.5 into 10 to the power minus 6 because it is in microsecond. Similarly, it will be 15 into 10 to the power minus 6. So you will get 15 into 10 to the power minus 6 into 2. And if you do the calculations, it will come 32.258 kilohertz. Okay, so that is the precessional frequency of the proton, okay, or the on resonance nuclei under the applied field B1. Okay, so one can find out that. Okay, or if we know this, we will be able to find out what should be the value of tau, or a value of like this. You can find out all these parameters if you know them. Okay, now we'll come to another topic called relaxation, and I have already told you because we are using this term throughout all the lectures from the very first day. Okay, so again I will just quickly remind you what is relaxation. Okay, so what you do when you put a external magnetic field B0, so this thermal equilibrium state population of alpha and beta state, they redistribute and follow the Boltzmann distribution. Okay, and then now if you put a radio frequency field, okay, pulse, okay, these spins become phase coherent and hence perturbed away from the equilibrium distribution. Okay, that all you have seen. So this is your now the Boltzmann distribution or equilibrium state population, and then if you put a B1 field, now you can see they have become phase coherent and it is now away from the z-axis. Okay, now once if you turn off the B1 field, then you will see the process by which the spins return to the thermal equilibrium called relaxation, and it is not instantaneous. Okay. Okay, so now there are two types of relaxation mechanisms. See, one thing is that when you are perturbing, you have the MXY magnetization, and when it goes back to the Z axis, that is called so there are two relaxation mechanisms are simultaneously operating. So one is called the longitudinal relaxation or T1 relaxation. It is a process by which Z component magnetization, okay, along the Z axis, it returns to its equilibrium value. Okay, you will see there is again the Z component magnetization will be less in this. Okay, and then slowly it is increasing again, going back to the equilibrium value. Okay, and the time constant for that is called T1. Another is called the transverse relaxation. It is also T2 relaxation, which describes the decay of the sea. As soon as you bring the XY magnetization, it never remains of the same magnitude. It decays with time. That's why you have seen your FID is decaying. Okay, that is because of the T2 relaxation. And that the transverse relaxation, and for that the time constant is T2. Okay, so now we'll talk about the longitudinal relaxation. It is a process by which, so what we have seen in longitudinal relaxation, that it is a process by which the Z component magnetization returns to its equilibrium value. Okay, okay, and that time constant is called the T1. Okay, so now again we'll be I am telling you this is your equilibrium state population. Okay, I will not and this is this delta is nothing but the energy difference between the two states, which is nothing again h mu, and this and these are the two constant, the Boltzmann, and T is the temperature. These are the things I have several times we have told. Okay, so when there is no magnetic field, both the state populations are same. But when B0, you are just applying B0, so it does not instantaneously reaches the equilibrium. So there is it takes time. Okay, so this re-equilibration is not instantaneous but governed by longitudinal relaxation time T1. Okay, and that only, this also I have discussed during my maybe first lecture or second lecture. This equation is there where n equilibrium is the difference between, see this n equilibrium minus nt is the difference between the equilibrium population and the population at the time we are describing, and 0 is the population difference at 0 time, and of course n equilibrium will be the population at t is equal to infinity, because that it will reach the equilibrium. And this thing also I have explained to you that the previous what I told you is shown here in the graph. Okay, so at the beginning you see that when time is equal to 0 and you turning on the magnet, the alpha beta states are equal, and you will see that this, as the time goes, it changes the distribution, and you will see that after 3t1 you will see there will be a clear-cut increase in the alpha population than the beta populations, which I have shown with a x plus 6, x plus 4, but these x, both x are very large numbers, so that depends. Although we can see it is more, but really the numbers are very less. It's 1 in or q in million. Okay, and if you keep it for 3t1s, you get about 90% of equilibrium is reached. And now if you turn off the magnet, again they will come back to the population after that. Of course it will take infinite time. It is like your first order chemical kinetics or first order decay. Okay, now that is one way of we described that from a zero state to the equilibrium, and from equilibrium state, and then suddenly if you turn off the magnet, again it is coming back to the ground state, okay, or normal condition. Okay, so there could be another possibility that initially your equilibrium population is there, you have applied magnetic field and then you left it enough time so that the magnetization is equilibrated. Okay, and now you give a 180-degree pulse. So what it will bring? It will bring all the magnetization to the minus z axis. Okay, so that's why you will have a minus mz t0, and then you just give enough time. Okay, so that what you will see, that as the time is increasing, the magnetization is decreasing, but still for some time it will be negative. It is decreasing from the negative value, but it is decreasing, but still it is negative. And then you will see that after a certain time that again it will go to the positive z direction. Okay, and theoretically it should take infinite time to again go back to the original position. Okay, okay, so this, so that you can see the magnetization is decaying in this fashion, and that can be mathematically expressed that mz at time t is equal to mz t0 exponential minus t by t1. T is nothing but the time which you are measuring. Okay, okay. And now this T1 is very important, as I told you. So T1, if you remember in my last lecture, I told you that T1 relaxation time determines the pulse repetition rate, okay, or TR. So how much delay should be given between two successive scans, okay. So that is one important thing. Otherwise, your spectra will get saturated. Okay, normally T1 for proton is around 0.5 to a few seconds. Okay, so it is quite fast. Okay, but T1 for quadruple nuclei will be very short. Okay, because of this quadruple nuclei is having electric dipole moment, and they relax very quickly. And then if you have your sample contains some paramagnetic substance, okay, you will see that T1 decreases drastically. Okay, so that is another problem. If your sample or if your molecule is having some paramagnetic center, you will see very broad lines. Okay, that's why in many, see, in oxygen is paramagnetic. That's why in many, when you do a very specific experiments, okay, where the paramagnetic system has to be completely removed, then you have to do a removal of oxygen by purging nitrogen in through your sample. Okay, and specifically we will see that when you measure the NOE, you have to remove oxygen. If it is there, you will not get a good NOE result. We'll see the NOE, and the next class we'll discuss NOE. What is NOE? Sometimes deliberately we add a paramagnetic substance into the NMR sample. Specifically when you are recording carbon 13, because we know that many carbon nuclei, they are very reluctant to relax. okay, or relaxation times are very long. So if you put these paramagnetic salts, their relaxation time decreases. Okay, so this is not normally done, but if you want to, in cases where you want to really integrate the carbon-13 spectrum, then you have to do all such kind of things. Now let us see what are the different mechanisms for T1 relaxation. So one mechanism, already I told you, the interaction between the magnetic dipole of a target nucleus with a fluctuating electric field of a quadrupole nuclei. So if you have paramagnetic substance, that actually they interact, your magnetic dipole of a proton or carbon-13, they interact with quadrupole, okay, or electric field of quadrupole nuclei, and can bring the efficient spin lattice relaxation. Okay. The other is the dipole-dipole interaction. So dipole-dipole means you have the target nuclei, that is a dipole, okay, and you have the solvent or the lattice, which are also mostly dipole. Okay. Okay. So now, so if you see your lattice nuclei, your solution, they are constantly moving, okay, or they are in a constant periodic motion. So their motion are due to rotation as well as translation. Okay, so when they are rotating or moving, so their local fields are also fluctuating at the same frequency. The frequency they are rotating or moving, that all the magnetic moments are also fluctuate at the same frequency. So when this frequency of this motion is comparable to the frequency of the target nuclei or NMR frequency of the target nuclei, so there can be a spin flip. Okay, so then there is a exchange of energy between the lattice and the target nucleus. That's why we call this T1 relaxation is also spin lattice relaxation, because the energy of the spin gets to the lattice by this way, or it vice versa. Okay, so these exchange rate is governed by T1 and continue until the equilibrium is established. Okay, so this interaction can be this dipole-dipole interaction can be expressed by a equation where the BL is the magnetic field of the lattice nucleus. Okay, the magnetic field due to the movement or the periodic motion due to the lattice nucleus with a magnetic moment of mu L. So this mu1 and mu L, and this theta is the angle between the B0 and a line connecting between the lattice nuclei and your observed nuclei. Okay, and this r is the distance between them. So it distance depends on the distance also and this angle also. And you will see that this equation will be keep on coming many times in solid state NMR also. Okay, so this is nothing but called the magic angle. Okay. Now, let us see effectiveness of the relaxation by lattice nuclei depends on the correlation time. I told you the movement of the or the motion. So where this tau correlation time is nothing but 1 by omega. So there are two types of correlation time. So one is the rotational correlation time, which is described the time required for a molecule to rotate by 1 radian. Okay. Whereas for a translational correlation time, so it is the time required for a molecule to move a distance of 1 molecular diameter. Okay, so the molecule is having particular size, so it requires that much distance it should move. So that means effectively the lattice nuclei magnetic field or magnetic moment is fluctuating, and that is creating a magnetic field called BL, which I have told in my previous slide. Okay, thus that this correlation time is in an average measure of how long two nuclear magnetic dipoles remain in appropriate relative orientation to interact. Okay, if their frequency match, that means they are interacting properly. With the frequency mismatch, then there will not be proper interaction. Okay. Okay, so this is the final equation that you can correlate the T1 relaxation time with the correlation time tau. So this 1 by T1 is proportional to the correlation time divided by 1 plus 2 pi nu 0. So nu 0 is the precessional frequency of your target nuclei, and tau c is the same tau c square. So okay, so let us say if the molecular motion is very fast, okay, so then you will see that 1 by tau c will be much greater than 2 pi nu 0, okay, or 1 by T1 is proportional to tau correlation. Okay, so that is the tau is inversely proportional to tau c. So you can see we have plotted here log tau c with log relaxation time. We have considered here both the relaxation time, because both the relaxation times are affected by this correlation time. So anyway, we will discuss only about this. If you see that when log that correlation time is small, okay, then also you will see that relaxation time is decreasing. Okay, so as the correlation time increases from very from very low value to higher value, you see the relaxation time T1 decreases, and then it reaches a minimum. At that minimum point, you will see that when this correlation time is equal to 2 pi nu, this will be 0 u0 to the power or 1 by 2 pi nu 0, you will see that it will reach to a minimum value, and then again if the correlation time increases, so you will see there is an increase in the T1. Okay, so for very fast molecular motion, okay, the tau T1 is inversely proportional to tau correlation. So as tau correlation is increasing, you will see that T1 is decreasing. Okay, and then it reaches to a minimum value, and then you will see that for the slow molecular motion, okay, you will see that 1 by tau c is much less than 2 pi nu 0. Then you will see that T1 is directly proportional to correlation time. You see here the T1 is, as the correlation time is increasing, the T1 is also increasing. Okay, and the minimum T1, okay, with most effective spin, that is relaxation, occurs where this is the condition. Okay, so that is the minimum T1. Okay, now as we have told that if this correlation time is a temperature and viscosity dependent and molecular size dependent, so T1 will also depends on all these three parameters: temperature, viscosity, as well as size of the molecule. We'll see that for larger molecule, okay, so larger molecules will be coming in this region, smaller molecule will come in this region, because smaller molecule will rotate very fast, okay, whereas larger molecule will rotate very slow. Okay, now we'll just finish quickly how to do this T1 measurement. So actually there are a couple of ways how we can measure the T1. Okay, so one thing is that already this equation I have told you, the MT, the magnetization along the Z axis at any time depends on the T1. Okay, so what you do, that means once you give you the pulse, it the magnetization come to y-axis, and then it decays. Okay, it decays, and that the Z component magnetization decays with a time constant of T1 and finally reach to its equilibrium, Boltzmann equilibrium value. And if you see that equation, that ln m0 minus mt equal to ln m0 plus t by, sorry, this will be minus. Okay, so if you plot that, so ln m0 minus mt, okay, so that means ln m0 is nothing, your equilibrium. Okay, so as soon as you give the pulse, you detect the signal intensity. So that is your M0. And then MT is you bring it to the XY plane and allow it to undergo the T1 relaxation and that value. Okay, and then if you sub that value you plot against 1 by that you plot against T. So you will see there will be a straight line. Okay, the slope is slope is 1 by T1. Okay, so if you know that, you can find out. So slope you can find out, and you can find out the T1. So this is one way. The most common way it is done is called the phase sensitive detection or spin inversion recovery experiment. Okay, now this again, it is the it happens along the z-axis. Those things are only being told. So and measure the automatically we will be measuring the magnetization along the z-axis. Okay, and the pulse sequence for this will be, we will give you a 180-degree pulse. Okay, and then we will allow it to relax. Okay, and then we will after that relaxation, you will see some of the magnetization will be reduced due to the T1 relaxation, and then you give a 90-degree pulse and you detect the signal intensity. Okay, and this tau is your variable. Okay, so as you increase the tau, you will see there is a more relaxation. Okay, so when you give the first pulse, it will go to the minus z axis. Okay, and then m is decaying exponential to m0, which the equation is nothing. It again m t is equal to m0 into 1 minus 2 exponential t by t1, like I told you earlier. But only thing is that we have added now 2, because see, when you are bringing it to minus 180-degree means you are bringing it to minus z. Okay, your magnetization, so it will go to, this is 1 m0, and then again it will go to plus z. That's why the 2, so it is a 2 times of m0. Okay, so the relaxation is not 1, it is a 2 times of m0 relaxation. Okay, and if you can measure when this is crossing this null point, okay, exactly, or you call that 0. Okay, then mz by t is equal to 0, because at this point it is 0, and then automatically you put that in 0, as m0 is not 0, you can find out that t1 is nothing but this, the time required to become this become 0, and it is divided by 0.693. It is just simple mathematics. Okay, and that only I have shown here. So if you give 180-degree pulse, okay, so it is bringing here, and then if your tau means your relaxation time you are giving to relax is less than tz, then still your signal will be, magnetization will be in the, along the minus z, and you will detect a negative signal. Now if you do give a 180-degree pulse, okay, so it will be at minus, and then if you the relaxation, if you giving enough time so that it is more than the this null point, the magnetization will be going to the plus z direction, and then if you record, you will get a positive signal. But when this is 0, okay, there will be no signal. So if you can find out this null point, you can very easily find out the T1. Okay, and this is the way it is done. You take the whole spectrum and do this thing, and if you remember in a NMR spectrum, each nuclei is having their own T1. Okay, it is not that the full molecule is having a single T1 value. Okay, so each nuclei will be having a T1 value with which is related to that nuclei. Okay, so for each nuclei there will be a T1, and so you see here for the example, you see that in this particular case, you see that almost this one is still negative, this one is still positive, but here see it is almost null. So you can see that, but other things have gone positive. So that means these nuclei here are relaxing faster. Okay, these they are relaxing faster than this nuclei. So if you want to give appropriate delay, you have to select the nuclei which is having the longer T1. Okay. So during setting up of your experiments, it is that T1 which you have to select. Okay. So I'll stop here. If you have any queries, you can ask me. Okay. So in the next class, I'll continue with the relaxation, because I will discuss what is T2 relaxation and how T2 relaxation is measured. Okay. So I'll stop here if you have any questions. Any question? Any doubt or any comment? Okay, so your next class will be on Monday at 4 p.m. So if there is no question or no doubt, then we'll stop here. You please put your registration, that is registration number, registration number in the chat box, so that your attendance will be recorded. Please do that before you leave the. Okay. Okay. Thank you.